Good morning, guys. So today we will see the numericals based on the truss element. Okay. In previous lecture we have derived the elementary stiffness matrix for truss element. Now in this lecture we will solve one example related to your truss element. Okay. Means we will apply our same procedure that we have applied during our bar element, spring element. Here we are going to apply same procedure to truss element also. So we will try to solve this example based on the truss element. Okay. So in this example, the example is given like that. There are the structure, truss structure contains 3 bars with areas as well as the lengths of this support or of this horizontal element is only given, and the vertical length is given here. This is the 400 mm. This is totally 800 mm. 400 plus 400, 800 mm. Okay, as there are 3 elements: element 1, element 2, element 3. And here it is asked to find out. First one is displacement at each node. Displacement at each node means as there are 3 elements, there are 3 nodes: 1, 2 and 3. So find out displacement at each node. Second one is find out the stresses in each member, means stresses in each bar element. The next is what? To find out the support reactions. Okay. So this is the example with all areas are given. Means area for this element is 1500 mm square, area for this element is 2000 mm square, area for this third element is given equal to 2000 mm square, and also a 152 Newton it is acting at node 3 in a downward direction. Okay. Also E is given, Young's modulus E is equal to 200 gigapascal for each element. Okay. So now we will try to solve this example by using our truss element theory. Okay. So as we know that for truss element there is a separate elementary stiffness matrix as we have derived in our previous lecture. Okay. By using this elementary stiffness matrices we are going to construct our global stiffness matrix. Okay. Then by constructing global stiffness matrix, then convert this into a force and displacement relationship. Then apply the boundary conditions. You will get the displacement first. Then by using these displacements you will get reactions as well as you will get the stresses in each member. Okay. So the procedure is same here. The only change is that we need to identify or we need to find out the elementary stiffness matrix for this truss element. Okay. So for this we need actually the elementary stiffness matrix for truss element. It is given by K is equal to AE by L into this stiffness matrix L square Lm minus L square minus Lm, M square L square M square. Okay, this is minus Lm, this is Lm minus L square. Similarly, Lm minus Lm, Lm minus L square minus L square minus L square minus L square minus M square. One second. Oh yes, exactly. Minus it is L square Lm minus L square minus Lm M square minus Lm minus M square minus M square. Then L minus L square minus Lm L square Lm, then minus Lm minus M square, M square Lm M square. Okay. So this is your elementary stiffness matrix or the truss element as we have derived this elementary stiffness matrix in our previous lecture. So we are going to use this elementary stiffness matrix to construct our global stiffness matrix for this truss structure. Okay. So in this way, now here L is what? L is nothing but cos theta. M is what? M is nothing but sin theta. So we need here first one is area, second one is azimuth, third one is length for this particular element. Similarly, we need L, value of L. Value of L is equal to cos theta. So we need theta. Means what is the theta for that element? Okay. So for this case, we need we need to refer. We need a reference system or reference global coordinate system. So here, select any node. Okay, select any node. We need to put this global coordinate system at this node, and by using this global coordinate system, we are going to find out our value of theta. So here at node 1, this is node 1, this is node 2, and this is node. So at node 1, we are going to execute our global coordinate system. It means we are taking this node 1 as a reference node. So at this is our global coordinate system. Let us say this is x, this is y. So node 1 is a reference point. At this, from this node or from this global coordinate system, now we will find out the values of theta for each element. Okay. So we need theta. By using this theta, you can calculate L, you can calculate M. Then we need length also, value of length also. We need area, we need azimuth. Now azimuth is common, 200 gigapascal for each element. Now area is also given for each element, for element 1, for element 2, for element 3. So area 1500 mm square, 2000. Okay. Now we need to find out first length. So this L1. So from this diagram, length we need to determine length. So actually we need to construct one table. So first one is 11, 1, 2, 3. Okay. Then next thing is length of that element. So L1 is equal to what? L2 is equal to what? And L3 is equal to. Then next is theta. So theta 1 for element 1, theta value of theta 1 is what? Theta 2 is what? And theta 3 is what? Then next, L is equal to cos theta. So L1 is what? L2 is what? L3 is what? The next is M is equal to sin theta. M1 is what? M2, similarly M3. Okay, so up to this we need to find out element length theta, L, M. Similarly, we need L square, we need M square, and we need LM also. Okay, because all these L square, M square, and L, all these values are in your elemental stiffness matrix. So we need to find out, or we need to first find out this table. Okay. So this table we need to construct initially. Now for this, first we need to find out the length. Now L1, L2 and L3. So this is your L1. Okay, so L1 is nothing but 400 plus 400. So L1 it will become equal to 800 mm. So L1 will become 800 mm. Then next, for second element, this is your first element, this is your second element, and this is your third element. Okay, so for second element, so find out the length for this second element. So how to find out this length for the second element? So look, so as we know that this vertical length is known, this horizontal length is known, 400, 400 means this triangle will become like, okay, this 400 we know, this vertical distance also we know, 400, and this is your L. So by using Pythagoras theorem, you can find out the value of L3. So L3 will become square root of this square plus this square. 400 square plus 400 square. So you will get L3 equal to, because this is a rectangle, so it is a rectangle. So we find by using Pythagoras theorem you can find out the value of L3. So L3 it is equal to, so L3 it is equal to 565.6. 565.6. So this will become 565.6. Similarly, L2. So for this L2, we will use this right angle triangle. By using this right angle triangle here, the length is 400, this length is also 400. So you will get this L2, it is same as L3. So L2 will become equal to 5, it is nothing but equal to L, because we are using same length, 400, 400. So by using this Pythagoras theorem, you will get L2 and L3 is equal to 565.6 mm. 565.6 mm. Now, next is what? To find out the values of theta. Okay, actually this truss problem, it is used for 12 marks in your end semester examination. So for this, we need to first construct this table. For this table only, you will get 3 to 4 marks. Okay, then for constructing your global stiffness matrix, you will get 4 marks, and then for